Hello everyone. For this video, we're gonna solve a question paper and of numerical analysis and design. And let's get started with it. For the first question, we have write an algorithm to accomplish the task for polynomial px given in the following table. You can see there is a polynomial given, and we have some tasks that we have to do, which is evaluating the polynomial that is given through brute force technique and recursive approach. Then again we have divide a polynomial by x minus r, again with the in both the techniques, and derivative of the polynomial with both the techniques. So to answer these questions, we firstly write the algorithm for the polynomial, evaluating the polynomial for the brute force. So firstly, the thing we have to do is uh, we have to initialize a variable called s. I mean, we would just initialize it. It would be the sum of all the terms, and so we would initialize it to 0, and next step we would just for each term of the polynomial from highest to the lowest degree. Okay, so we have to provide a for loop. I mean, we have to start a for loop for the polynomial from the highest degree and to the lowest degree. Now, what is the highest degree? We have to take it from n, uh, n to the n till 1. So that's how you have to do it. Means you have to decrease the for loop. You have to decrease the for loop in a of the polynomial. You have to decrease the degree. For that you have to use a decrement for loop. And so and to the next step, which is compute the value of the term by. And now that we have the polynomial, we have to if we have to generate the term, we have to first do the multiplication of the coefficient with x, obviously. I mean, we have the polynomial, right? So to get the desired term, we have to firstly multiply the x with the coefficient to raise our degree of the term. I mean, if we have xn, so xn should be multiplied to the an. I mean, an is what? An is our coefficient, and xn is our argument. And so we have to um, multiply the x with the coefficient until it raises the degree of the term, and then the computed value would be uh, assigned in the sum variable s, and we would just return the value of the sum variable as the value of polynomial that was there, px. On to the next on to the next procedure, that is recursive approach. Here we would just the process is same. It's just we need to have some recursion approach. And so firstly we would check if the polynomial is the degree of polynomial is 0, the value of term the value should be a constant term that should be returned. I mean, if the degree is 0, then a constant term should be returned. For the second method, you have to compute the now you have to compute the px recursively. And so to do that, we have to compute the degree. I mean, we were provided with it, right? We have to keep it till n. So for that we have to compute the value of the polymer till it is the degree of n minus 1. And how can we do that? We have to call the function recursively till uh, with the polynomial that has n1 minus 1 as argument. Computing the value of the current term by multiplying the coefficient. The next term we have next thing we have to do is computing the value of the current term by multiplying again the same process that we did earlier in the brute force, that we have, if we have to generate the term, we have to multiply the coefficient with the x to raise our degree of term, and then again and the same procedure that we did earlier, that was adding the computed value to the polynomial so that we can have a returning value as px. Now on to dividing polynomial by x minus r. So for this we have a question polynomial. Obviously when we divide a number we have a quotient, we have a remainder that is r, and both the variables should be initialized to 0. Now for the polynomial again we have to uh, decrease the degree of the term every loop, and so for that we will use a for loop for the next. And the first step after that is just we would just compute the value of the current term of the coefficient by dividing the coefficient. Okay, so now what do? We will just use the polynomial and divide it. So we, after dividing the x by x minus r, we would get a coefficient term, that is the term that we have to generate. Now the compute, now that we have got the coefficient quotient value, quotient polynomial, we will just assign it to the q that we have initialized. On to the remainder part. Now the remainder part would be multiplied to the quotient of the current term with x minus r. So the remainder that we have now, I mean we get both the things, right? We get a quotient, we get a remainder, and so to do that, the remainder would be multiplied to the quotient that we have generated, and after doing that we have to subtract the computed value from the current term of the polynomial. Once we multiply the remainder with the quotient, we have to subtract it from the polynomial, the first polynomial, as in the initial polynomial. And after doing that we have to keep it in the remainder r, and return the quotient and r value in the last step. For the recursive approach, again we have to do the same thing. We have to check if the polynomial is 0. If it is 0, then we have to return the constant term. Otherwise, we have to compute the value of px recursively. Again, we have to compute the value of polynomial of the degree by calling the function recursively with polynomial of degree n minus 1 as argument. Okay, and so then we would get the q, like in the above procedure we said, I already said that we have to generate a q, and after generating the q we have to multiply the we have to assign that value to the q that we have initialized, and then after computing the value, we have to now multiply the quotient with the quotient of the term that we have got, quotient term that we have got, the remainder with the quotient. Again, I'm sorry for that, remainder would be multiplied to the quotient, and then it would be subtracted from the current term of the value polynomial. And after doing that we would just uh, assign the value to the polynomial n, and adding the computed value to the polynomial of degree n minus 1. After adding, we would just return the quotient r and quotient q and remainder r. For the derivative approach of derivative of the polynomial px, firstly we have to initialize it. Obviously for derivative, we have to initialize the d first, and it would be initialized. Again, for the polynomial decrement, we have to keep a for loop for that. Inside the for loop, you have to um, we have to compute the value of the derivative by multiplying the coefficient of the degree and subtracting it from, like, we have x, right? We have the coefficient, that is a, and we would just add compute I'm sorry multiply the coefficient with the degree of the we would just, like, we have the coefficient, and the coefficient that is to be computed with the x that we have got, okay. And so we would just compute the value of the derivative of the current term by multiplying the coefficient with the degree of term and subtracting 1 from the degree. Obviously, as there is we have to decrease the degree, and so for that we have to subtract from the 1 from the degree ever once in a while. And after doing the computation, you just have to assign the value to the polynomial d. Again, for the recursive approach, we have to check if the polynomial is 0 or not. If it is, then we have to just return the value. Otherwise, otherwise we have to compute what the derivative of polynomial recursively by computing the value of the polynomial by of degree n minus 1 by calling the function recursively. We have to call the function recursively. Then we have to just in the um, we have to just compute the value of the derivative of the current term by multiplying the coefficient with the degree of term and subtracting 1 from the degree. With this, we would just compute the value of the derivative polynomial d, and we would just add it and just return the derivative of the polynomial d. With this, we just started. The question is, write the algorithm flowchart of the following task and complete the table. As you can see that I've already completed the table, where there was given a task where we have to subtract uh, two numbers, and then it was given some two datas, where we had n1 and n2 for each of them. Then if you have some errors or messages when we calculate them, I have to write that error and messages. Um, and finally, I have to write the final result of the data after computation. And so you can see that it was firstly I did the subtraction, the secondly I did the multiplication, and thirdly I did the division. And so I reached a final result with some errors that I could find. And we were told to make the flowchart, and so I would just show you that. Okay, so firstly we have to start and read the values of n1 and n2, where we would see that if e1 is equal to e2 or not. If it is, then we just have to make sure that we just add or I'm sorry, it's just we would, here it is written in minus. I just change the sign when it comes to I'm sorry for that. I would just change this plus into the minus. I mean, I would just change it to. I would just change the sign for subtraction, and so it would get me an answer like I would just subtract the mantisas and uh, just take the value for any the error part, the exponent part of the number. After that, if it is not equal to e, so the another possibility it can be the e1 is greater than e2. So if it is if it agrees with that statement, we just have to shift m2 by e1 m2 and by e1 minus e2. This is an exponent formula that we use when e1 is greater than e2. And after shifting, uh, we would just create the we would just subtract the Mantissa part and take the e1 as the exponential part of the new computed value. For even being not greater than e2, like the not part of this generalized getting generalizing the exponents, if it is the no part, then we would just shift m by e1 minus e2 and just take the value we would just shift m1 by e1 minus e2 and we would take the Mantissa again and we would take both the Mantissas, like we would subtract both the Mantissas and even would be taken as the exponential form. Now consider that we have the condition as um, the E1 was is equals to E2, and so we went for the normalization. For that, we just subtracted both the Mantissas and took one of the exponent as the computed exponent, and now we have to just generalize it. We just have to generalize it. If it is generalized, so we would just print the number, the computed value, and just stop with it. If it is no, we just have to normalize by shifting the m by points that have been there, like 0 of 1. If it is like minus 99, I mean if it is greater than that, so we just have to shift one of the Mantissas, like considering all the amount for you just have to shift one back or shift ahead one, adjusting all the exponents. And that's how we would just normalize when it comes to generalizing the number. I mean, the new computed value from here would be first generalized. If it is already generalized, then we would just print it. If it is not generalized, we would normalize it first by shifting the decimal point of the Mantissa part by adjusting the exponents. Now, how do we do that? Now, if the E is greater than 99. If the E is greater than 99, we have to print the overflow error. If it is no, I mean the E is less than minus 99, then we just have to print underflow error. With this, we will just get the answers and as A and B, and so this is how we would do the subtraction part of the question. For the next one, this is for the multiplication one. We will just go. Let me just increase the yes. And for multiplication again, we will just start and then read both the numbers. After reading both the numbers, we would just multiply both of them. Like if the thing we did before generalization, we just multiplied it. We won't see if we won't compare the exponent part of the numbers. We would just directly multiply both the Mantissas and add both the exponents. Like what do we do with the exponents in normal mathematics? We would just add the exponent, and if it is division, we will just subtract the exponents. That's how we do here also. And if it is now, let's say if it is normalized, I mean it is already generalized, it is normalized at the same well, I mean to say is generalized or normalized as the same thing. And so if it is already done, I mean if the normalization is already done, we would just print the number and stop with the whole algorithm. If it is not generalized, we would again shift all the points in considering all the Mendesa part, and the Mendesa would be adjusted according to the exponent. Now, if there is this exponent which is if the exponent is greater than 99, again we have to print the overflow error. And if it is not greater than 99, it might be the error maybe less than minus 99. In that case, we would just print underflow error, and that's how we would just go for the multiplication part of the question. Again, with if it is the division part of the question, like the task, would firstly, like we would just start with it. Then we would take the numbers, we would divide it, like we would divide the Mentisas and subtract the exponent part. Again, if it is not normalized, we would just normalize it by shifting the decimal point of the of the Mentisa part, and adjusting all the exponent. I mean the whole shifting the decimal points in the Mendesa part is done so that we could adjust all the exponents that we have in like we have to keep both the exponent of a number same. And so to achieve that, we have to adjust the Mendesa and shift the decimal points. And if it is normalized, I mean it was already normalized, so we would just print it. And during normalization, if the error is again 99, I mean it was there, the error was more than 99, we have to print the overflow error. And if it is not it is less than minus 99, it would print the underflow error. And that's how we started. The question question 3 is verify associative law and distributive law of arithmetic with fitting 4 and Mendesa digit and provide correct answer if no number is truncated. So we have two cases which we have to prove as written here. We have to prove both the laws with the given data. And so I can show you that I have already done that. Let me show you. Yes, this is the calculation that I have done. I mean, I just firstly uh, firstly I have taken the values, then calculated a plus b. I got a single value. Then again a plus b minus c for this part of the equation. To satisfy this equation, I have done this. Then to prove again, I have done a or c value, and then a minus c plus b value. And finally you can see that the values are not equal, and so the law is not working in this case. It is said that the LHS is not equal to RHS, and we could say that I have already shown you the calculation. And the distributive law is also does not hold for these values, and therefore for case 1, both associative law and distributive law both do not hold any of their values. For case 2, I can show for case 2, I can say, like I can show that case 2 has another law here which we have to prove, having a as certain b as a certain value and c as another value. And so I can we can see the another value for this. Uh, okay, so again I have tried the law and computed the values, which has b minus c, and generated the value again a into b minus c to get the first value of the equation 0.550 e minus 1. And then again the another other part of the equation I have tried to satisfy, which at the end of the day did not work out. We as LHS was is not equal to RHS, and so we could say that therefore ABC and A B minus C, both the associative and the distributive law for case 2 does not hold any of the values, and so since no law holds for these values, we cannot provide a correct answer without truncation. Okay, so that was video. We have question number 4, where we have to state whether the statements written here are true, either true or false. So let's get started. The first question is minimize the number of arithmetic operations whenever possible. Now, if we minimize the number of arithmetic operation, uh, you can have more efficient programs. I mean, if you have a less number of operation, the processing time of that operation would be also low, and with that we can increase our efficiency, so the program would be more efficient. Considering accuracy, if we have minimized the number of operation, overall error the overall error would be also reduced, and that would improve our accuracy. Considering the memory usage, if we have small amount of arithmetic operation, the minimal amount of arithmetic operation, the memory use would be also less, and so I think the we should always minimize the we try to minimize the number of arithmetic operation, which would lead to efficiency, it would lead to more accuracy, and try and will have less memory usage, and so the statement is true. For the next question, we have avoid taking the difference of two nearly equal numbers whenever possible by altering formulation of problem. If it cannot be avoided, then take the differences before doing other uh, operation. Now consider two numbers that we have here as A and B, as you can see here. Now if we subtract both of them, do you think the value of C would be very big? It would be very small. Considering A and B are very near to each other. Those both the points are very nearly equal to each other, and this could lead to inaccurate result. And so to avoid this problem, it is recommended to use an alternate formulation of the problem that avoids taking the difference of two nearly equal numbers. This can involve algebraic manipulation. I mean, you can just manipulate or reorder the calculation to reduce the sensitivity to small changes in the input. It is not possible to taking the difference of two nearly equal numbers. It is recommended to take the differences before other operations. So when we subtract two nearly equal numbers, it is our it should be our focus that it does not create more that it should be avoided before taking any measures. I mean, you have to do other operation, then do this operation. So I think that the second question, I mean the second point of second statement is also true. For the third statement, we have adding or subtracting numbers starting with the smallest number and works the number in ascending order. For example, we have A, we have B, we have C and D. Now we add these numbers in descending order. Okay, and then we think about in ascending order. You can see if this is the case, adding the small numbers first reduces the impact of rounding numbers. I mean, if we just go for a descending one, we can see that the impact of reducing the error, uh, if we just add the small numbers first, the impact of rounding numbers would be reduced, and the accuracy of this operation would be more improved. And so I think that adding and subtracting numbers, starting with small numbers and working with number and works with numbers in ascending order is true. For the next question, do not formulate an algorithm that tests whether a floating number is equal. It is not recommended to formulate an algorithm that tests whether a floating point number equals 0, because floating point number are not exact. Their value may be subject to rounding number. Due to the limited precision of floating number arithmetic, it is difficult to represent certain number exactly, including 0. This means that even if two floating numbers are mathematically equal to 0, the representation in memory may differ due to rounding numbers. Instead of testing whether a floating number equals to, it is better to use a threshold or tolerance value to check whether the absolute value of the number is sufficient or not. So this statement, do not formulate an algorithm that tests whether a floating point number equals 0. This is true. For the next question, ill condition of problem is normally due to improper formulation, can be eliminated by carefully reformulating the problem. A practical way, if detect suspected ill condition, is to alter the parameter by a small amount and observe the effect on the solution. This question is true. This statement is partly true. I mean, ill condition of a problems can be due to improper formulation, but it can also be due to the nature of problem itself. So this statement is partly true. And for the with this we just we should start with the question number 6. After a numerical algorithm is obtained, check if it can lead to numerical instability. In such a algorithm, error grow in each step of the calculation. In such a case, reformulate the solution procedure to get a stable numerical algorithm. The statement that it is written here is it is partially true, because yes, obviously numerical algorithm can lead to numerical instability, and errors can grow with each step of the calculation, and it can be through various measures, like it can be due to ill conditions, it can be due to rounding of errors. So to ensure that you have to ensure numerical stability, instability, it is important for us to analyze the algorithm and implement it, and the potential identify the potential. I mean, just have to carefully analyze the algorithm and try to find if there is numerical instability in potential source of instability or not. मतलब, like like the instability is there or not. And to do this, you just have to test the algorithm on different range of inputs, and you have to check the behavior, and that's how you would just check for numerical stability. If there is numerical instability, we would just reformulate the whole numerical algorithm, which has different methods. And so while doing this, you can see the impact of rounding the errors, and you can just see the numerical instability being detected. And therefore I think when you're writing a numerical algorithm, it is necessary to check for a numerical instability, and for that matter, sixth question is true. And for the seventh question, if severe rounding errors and consecutive loss of significant digit is anticipated, and if no alternate formulation to avoid this is possible, then carry more insignificant digit in the critical calculation using floating point number in double precision mode. In this mode, the length of the mantissa is twice that of the other floating point quantities. The statement is true. Severe rounding off and consecutive loss of significant digit can occur. Obviously, when we are doing numerical calculation, we do have some severe errors. We have to consecutive severely round off all the errors. We have to consecutive. We have to have some losses of significant digit, and so particularly when dealing with a widely magnitude and performing operation on values that is close to limit of machine pre- precision. However, to achieve this in double precision, which allows for the twice number of digit in the mantissa compared to the standard floating point number. This can help to increase the precision of the critical calculation and reduce the potential of the rounding errors. So it is the seventh question is actually true. And for the eighth question, double precision requires large memory spaces and slow down calculation. Now this is partially true as whenever we considering a standard precision and a double precision, it would take more memory, and as it has more slow calculation as specific to its content and computational requirements, and as it requires more computation. Yes, obviously, to have more accuracy, have to compute more and try to have more space, as and so double precision requires large space, as it the desired level of accuracy is to be achieved, and to avoid our numerical instability caused by rounding errors. In these situations, the benefit of increasing precision may outweigh the additional memory requirement and computational cost. And so it is true that double precision requires large memory space and slow down calculation. In the third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.003. You can see through the computational here. I mean, it is computed in the whole the whole um, um, square root of 5 is computed here, and you can see the relative error which is measured. And so with this notation, I mean with the whole computation, you can say that the third approximation of the square root of 5 using the Newton-Raphson method with a starting point of 7 and relative error of 0.0 is approximately 2.24 and 99. We need information, and so it is assumingly not true. I mean, it's not true. Approximately. The whole question in the ninth question is true, as we can say that the relative error is 0.0013. For the last question, that is the 10th question, the iterative method are compared on following parameters: the rate of convergence, the amount of computational effort per iteration, sensitivity of the methods to the starting value and the intermediate value. Okay, so iterative methods does look after the rate of convergence. We have different methods of iteration just to see the rate of convergence. Now, what is rate of convergence? Rate of convergence decide uh, when we would get consecutive two similar values during an iteration. When two iteration have equal values, it means that the method has already converged. And so, considering iterative methods, the rate of convergence is very necessary. And for iterative methods, the rate of convergence is followed. For the second one, the amount of computational efforts per iteration. Yes. Considering bisection method or any other methods of iteration, you can see that in bisection we do a lot more computational, we put a lot more amount of computational efforts per iteration. We just, for other methods, we do not have to go a whole lot of computation as per bisection. So yes, when we talk about iterative methods, one of our focus is to see the amount of computation efforts that we require per per iteration, and sensitivity of the method to the starting point and the intermediate values. Yeah, sensitivity of the methods states that how starting point and the intermediate points have are sensitive to each other. This refers to the how sensitive the method is at the starting point and at the intermediate points. And so it is required to know the sensitivity between the both the values to for the iterative methods, and so the 10th question is correct. Thank you for watching this video. We are at the end of the question paper.